This is the first of several videos I will look at material from Math 243 as Stats 1 course. The goal of statistics in general is to take a small amount of information and then to extrapolate that to make a conclusion about a larger population. There are going to be a lot of things that we have to figure out on the way to that goal. I'm going to have to figure out exactly how do I look at data, how do I analyze it with, say, averages and standard deviations, how do I come up with graphs, how do I collect that information so I don't have biases, how do I make data models so I can make limited predictions about what should happen in really controlled circumstances, and finally, how do I build this all up into something called a confidence interval, which is going to give me a way to guess what happens for a population based off of a sample with a certain margin of error wiggle room. And you may have heard that term margin of error before. We are going to build up to that. This particular lesson just looks at data and forming questions. I'm calling that hypotheses. So first thing to kind of start out with is just sort of a definition of data. Data are information about a population. Technically, the word data is a plural, so data are is better grammar than saying something like data is. I'm not going to be that picky about this. In fact, this might be the only time I refer to this thing as a plural. Technically, datum is the singular and data is the plural. For those of you that are really careful about that sort of thing, I just want to be cognizant of it. There are two different types of data. There is categorical or qualitative data. The base quality here should be telling you a little bit about what it is. This is word-based data. In contrast, quantitative, the base here is quantity. This is number-based data. So let's look at some examples. A researcher records the color of every car in a PCC parking lot. For example, the color red. What type of information is this? Well, this seems like this is word-based data, so I would say this is qualitative. I'm describing a feature of cars, a whole category of things. That category happens to be color. So I could also call this categorical. Teacher for a stats course records the number of credits taken by PCC students in their class. What type of data is this? This feels more number-based to me. As a result, I would call this quantitative. Records the zip code for every individual that they pull over. This one's a little bit weird because it almost feels like it's a combination of both being a number and a category. I am going to err on the side of calling this thing quantitative, because it is still a number like 97229, but quantitative, it really feels like it's a special kind of number. We'll come up with more distinctions later, but I'm just starting out with this. Let's try another one. An inspiring meteorologist records the temperature every day. What type of data? Okay, try pausing the video here for a minute, looking at this, and ask yourself, does this feel like word-based or number-based data? So again, just pause the video for 2 or 3 seconds there. Does this feel like this is word-based or number-based data? Okay, and this might drive some of you super, super crazy. I'm going to say that I think this is qualitative. And for those of you that are thinking, what the heck, I know this is a number, something like 27 degrees Fahrenheit. Okay, fine, but I still feel like I can do this using words. So for example, for qualitative, if I wanted to talk about temperature, I could say cold, warm, or hot. In fact, if you want to convince me that it's quantitative in a situation like this, where you're saying something like 70 degrees Fahrenheit, the important part of this quantitative information is units. So as a general note, if you don't include units, I don't know if you are talking about word-based information or number-based information. And that's a big issue, because if I have 2 different people going out and collecting data, and one person is just writing down the words cold, warm, and hot, The other person's out there with an actual thermometer measuring things, and they try to bring their information together, they wouldn't be able to do so because quantitative and qualitative data are two very different things. I'm going to expand on this just a tiny bit more. And just to note, this is really just sort of the surface introduction about data. I could spend an entire term talking about the different classifications of data. I'm only going to be spending a couple of minutes here with you. So there are two types of quantitative data. That's that number-based data. There's something called continuous, and there's something called discrete. Continuous, this is anything that happens on a continuum or anything that's kind of like on a scale. So for example, if I have weight, I can be 135.2 pounds. As a really, really rough definition, you can think of continuous as having decimals. Discrete is anything that has jumps to it. So if it's possible to have like 101 and 102, but you can't have like 101.27528, something like that would be discrete. So whole numbers is what we will consider discrete. This is a slight lie because discrete really just means that it has jumps. So for example, shoe sizes I would still consider discrete because you can have 8, 8.5, and 9. It doesn't happen on a continuum though, so that doesn't mean you can go into a shoe store and be like, I would like an 8.275. That is the size of my foot. You would have to order somewhere on those discrete jumps. Let's go through these different types of data that I have above, and let's just categorize them as being either continuous or discrete. So number of credits taken by a PCC student. This is discrete. You can take 12, you can take 13, you can't take 12.4. Zip code 98685, 97229. These are whole numbers, these are discrete. Temperature, something could be 98.6 degrees, so that could have a decimal. So temperature would be an example of something that is continuous. I'm going to give you two more definitions here. Identifier and ordinal. Identifier, this is a number that uniquely identifies a specific category. And an example of this might be something like a social security number. If you give me a social security number, please don't give me your social security number, it would uniquely define who you are. Driver's license numbers, that's something that uniquely defines that person. Going through this, number of credits taken by a student, that's not an identifier. If I say 12 credits, I don't think, oh, that's Samantha. Samantha's a 12 credit person. It could be a lot of different individuals. Zip code, however, I would say is an identifier. You tell me 97229 and I'm thinking Portland area. You tell me 98685, I'm thinking of Vancouver area. So if you were thinking that this was some sort of a almost categorical piece of information, that zip code, identifier is sort of that bridge between the two. Temperature, 70 degrees Fahrenheit does not uniquely define what day I'm looking at, so I would not define that as an identifier. Ordinal, this is a number that is on a scale, something like a pain scale of 1 to 5, a Likert scale. So if I say I have a pain of 1, that's recognized as meaning very little pain, where if I say I have a pain of 5, that's recognized as having an extreme amount of pain, or 1 to 10, or whatever your system may be. So if you have any sort of number where there's a natural order to it, ordinal, the base there is order. So looking through these ordinal data there for a number of credits, a little bit of a stretch, but yes, little credits to a lot of credits. There's some sort of an order to those numbers. A zip code, this might not be obvious, but this is actually ordinal. I'm just going to leave this with the big question of why. I'm going to understand it, like underline that thing like 3 times there. Zip codes being ordinal, I think it's kind of an interesting example, and it's one that I want you to get your hands a little bit dirty to figure out as to why that's exactly the case. So try pulling up a map of zip codes for the US and see if there's a relationship for how those zip codes are aligned. So it might be a certain situation where all of the large zip codes are on the north or top part of the US, and all of the larger or smaller ones are in the south, whatever the case may be. I don't know. Try looking at a map and seeing, is there some sort of an order to zip codes? I'm telling you that there is, but try to figure out what that relationship actually looks like. Okay, again, I can get real deep in the weeds on all of this, but the point is that I have a lot of different ways of describing data, even with just words, without even consider the symbols or the arithmetic or anything else besides that. So the next part of this, let's look at symbol ways of representing data. So data is often summarized using numbers. We might be curious about a proportion or a probability of an event, the average outcome of an event, or the spread of the event. When I'm talking about spread, I'm going to be using language of standard deviation. And this is going to provide 2 new definitions as well. A statistic is a number that describes a sample. The way that I remember this, S for S. Statistics describe samples. So if you're taking a statistics course, you're dealing a lot in sample information with the hope of trying to figure out something bigger. Parameter is a number that describes a population. So in my head, what I'm kind of visualizing here, I'm thinking of this box as representing a large population. A sample is a group that sits inside of a larger population. And if I know enough information about this small little circle, I might be able to figure something about that box in its totality. Here are some examples of statistics, numbers describing a sample. I'm going to have symbols talking about the average. I'm going to have symbols talking about the standard deviation. And I'm going to have things talking about probabilities or proportions. So if I'm talking about a sample average, the symbol for that is an X with a bar above it. Statisticians are either really bad or really great at naming things, depending on how you think about that. We just call that X with a bar. Sample standard deviation, the symbol I use there is S. S for standard deviation. If I'm talking about a sample probability, the symbol that gets used is P with a hat. Again, not great at naming things, so I will literally just call this P hat. P with a hat. Populations. The symbol that describes a population average is the Greek letter mu. Statistics tend to be Latin letters, parameters tend to be Greek letters. Standard deviation for a population, this parameter looks kind of like Charlie Brown there. And this is called sigma. And finally, population probability population parameter here, the symbol P. It's really good to practice all 6 of these symbols because they're really loaded statements, and we're going to have formulas throughout the term that involves a combination of all of these things. So if I can't tell the difference between 30 people and 7 billion people, I've got some issues. Let's look at some examples where we're just labeling things with proper notation. So Coca-Cola has a contest going on. They claim that individuals should win 1 in 4 times. Now, this is for everyone. It's not like they call me up and say, John, here are your special individual odds of winning the game. This is for all individuals. And if this is for all individuals, then I'm dealing with a population. So I have a population. This isn't an average or a standard deviation. This is the proportion of people that win, 1 in 4. So my population probability, the symbol there is P equals 1/4 of the time. In contrast, I played the game 10 times. I could play the game more if I wanted to. And that's really a defining characteristic of a sample. Samples have this dynamic nature to them. So this is a sample. So I'm going to be using a statistic. My sample success rate, the symbol there is P hat. I won 3 times out of 10 plays. So I have a 30% success rate for the sample compared to a 25% success rate for the population. Let's look at another one. The average weight of all cats is 54 pounds. All cats. So when I'm seeing this and I hear 54 pounds, I'm thinking, house cat weighs 54 pounds. But this includes stuff like lions and tigers, these big, big game cats. So this population that I'm dealing with is going to have a much larger average because of those larger species. And it's also going to have a larger standard deviation than, say, just looking at 2 or 3 animals because those weights vary considerably. So population average for all of the cats, population parameter, average, I'm using the symbol of mu, 54, and I'm being really careful. If I have units, I'm including them. Standard deviation for a population, standard deviation for a population, sigma is 10 pounds. I have 2 cats. You'll see them sometimes running around in the background here, Victor and Fiona. They have a sample average of 13 pounds. I don't have all the cats in the world. I just have 2. That's why it's a sample. So when I'm describing this average of 13, it's for a sample, it's an average, it's an X bar. They have a standard deviation for a sample of 2 pounds. The average weight of my cats is considered to be less than the average weight of all cats because if it's all cats, it has some of those really, really big cats, and their weights don't vary that much. They're both pretty much the same size. Let's look at another one. TriMet claims that the train should be arriving at the station on average every 5 minutes. Sarah notices an average of 10 minutes for limited visits. So this here feels like a claim about a population. Or you might even say sort of like a population of interest. On average every 5 minutes. So average for population, that's mu equals 5 minutes. In contrast, she's seen an average of 10 minutes for her limited number of visits. So for the sample data here, she has a sample average, an X bar of 10 minutes. Now, eventually what I want to be able to do is, knowing information about the sample average of 10 minutes, I want to be able to guess what the population average should be. So I want to be able to use this right side of data to try to figure out what's going on with this left side. And part of this involves just phrasing questions properly. So let's look at forming hypotheses. Forming hypotheses determines how you're going to collect data. So for an example, a teacher at PCC wants to determine if a new prereq course is effective. In particular, they want to see if students are successful in their next math course. Why might it be a good idea to form a question and investigation before looking at data? This is a very open question, so let's just brainstorm. And in that spirit, I'm going to ask that you pause the video for just a minute or two here and list down a couple of reasons why you think it might be a good idea to form a question of investigation before starting to collect or look at data. Okay, I'm going to give you a couple of the reasons why I think this might be a good idea. Success is hard to define. So for example, maybe I'm looking at the percentage of students that pass the class. Maybe I'm looking at the average letter grade. Maybe I'm looking at the percent that graduate. Maybe I'm looking at the number of tries to get through it. For example, maybe the pass rate for 243 courses goes down if we change the prereqs, but more students are graduating because they don't have to take as many math classes. That could be defined as success. Maybe it's the case that I'm really strictly concerned about the pass rate. And if the pass rate is above a certain amount, I consider it to be successful, and below, I consider it to be not successful. The problem here is if I don't phrase the question ahead of time, I don't know which piece of information I should really be collecting. And if I'm forming my question after looking at my data, I'm going to end up with a whole bunch of false positives and false negatives where I assume there's a relationship where there's not really a relationship. You always form a question before you look at data. And when I'm forming these claims, they are typically about populations. So I'm going to use this phrase again. Claims are about populations of interest. And if they're about population, they're going to be involving parameters. So labeling values. PCC instructor from earlier claims that 70% of all students under the new prereq will pass the course. So this sounds like they're defining success based off of pass rate. So all students, population of interest, it's a probability of 70%. Now, I might want to use sample data to test that. So if I have a sample success rate of 65%, is that close or not close? What if it was 72? Is that considered close? These are questions that we'll be able to answer later on in the term. But I'm just trying to set the groundwork for what's coming up. How do I know when my sample and my population claims are close? How do I know when they're far away? Let's look at another one. Label the values using proper notation. This is the TriMet one again. Train should be arriving to the station every 5 minutes. I call this my initial claim, and the technical term is the null hypothesis. So here I would say the null hypothesis, my initial claim is that the average amount of time it takes is 5 minutes. When I'm writing down claims, it's always going to look like the null hypothesis. Null, this represents there being sort of no change. If I null a contract, there's no value to it anymore. If I null a bank account, it's at 0. So this represents things kind of staying static. So null change, and typically this represents a fair situation. HO colon mu equals 5 minutes. It's always going to be null hypothesis parameter, and it's either about averages, so I'll have the symbol mu there. It could be about standard deviations. I would have the symbol sigma. Or it could be about percentages or proportions, and I would have the symbol p. If the null hypothesis is not true, I need a backup so I can sort of establish what not fair is. So for example, if Coca-Cola says I should win the game 25% of the time, and I won 40% of the time, I'm probably not going to complain about that being unfair because I'm winning more than anticipated. If I only won 10% of the time and they said it should be 25, I might be a little bit upset in that situation. So in addition to the null hypothesis, I have something called an alternative hypothesis as a backup if the null ends up being unreasonable. These are a package deal. So what I typically have is a null hypothesis where I'm establishing what it looks like if it's fair, and I have an alternative hypothesis telling me what it looks like if it's unfair. I'm going to spend a little bit of time trying to phrase the null and alternative for a couple of scenarios. So previously, 80% of Comcast customers were satisfied with their service. They want to test if they've improved. So this is about percentages. I'm always going to be using p, mu, or sigma. Says 80%. So if there has been no change, 80% of Comcast customers would still be satisfied. They want to see if they've improved. Well, if they've improved, this would mean more than 80% of customers are happy with their service. This alternative hypothesis is always going to have one of three symbols. It's either going to be less, more, or different to the number that's being claimed. How do I know which symbol to put here? Well, it's going to matter a lot on context. So let's look at another one. Last year, the average flight, average for a population, I'm thinking of my symbols here. Average population, this is going to be about mu. Of a Delta flight from San Francisco to Portland was 90 minutes. They hope that they've improved. Improved means more efficient. So if things have stayed the same, if there's no change, then the average length of a flight is still going to be 90 minutes. If they've improved, that means that they've gotten faster. The flight would take less time, less than 90 minutes. There's no buzzword that absolutely tells me for sure which way these symbols should be. So for example, here improved meant more, and here improved meant less. So context matters a lot when determining your hypotheses. You want to test if a coin is fair. Well, let's think about what's going on with the coin. A coin has two sides, heads and tails. If it's a fair coin, I'm getting heads 50% of the time. I'm getting tails 50% of the time. So null hypothesis will say getting heads 50% of the time. Let's think about what an unfair coin might look like. If something had both sides of the coin being tails, then I would get tails 100% of the time and heads 0% of the time. That would be unfair. If I had a two-sided coin where both sides were heads, then I'd be getting heads 100% of the time. That's also not fair. So there are two ways in which this can be an unfair coin. If it's anything other than 50%, it's not fair. Again, if I have something like equals 0, this means that I never got heads. That's not fair. If I have something like p equals 100%, this means I always get heads. That's also not fair. So this does not equal symbol, this tests for kind of two things at once. It determines if there is a difference. A ruler manufacturer states that measuring sticks have a standard deviation of 0.01 inches. This is akin to the amount of air. So maybe these things sort of get larger or smaller depending on temperature. You think the actual amount that it varies is less than 0.01 inches. So null hypothesis, the spread is equal to 0.01 inches. Alternative, I think the actual amount it varies is less than 0.01 inches. Population standard deviation, sigma. I have fair, I have unfair. I have framed this thing as a proper question. So taking inventory of where we're at on all these pieces. I now know that there are several different types of data. There's quantitative, that's the number data, and there is categorical or qualitative, that's the word-based data. I have several symbols for looking at data, whether that be a statistic or a parameter, and I have ways of forming the questions. These are all great steps to getting ready to do some heavy data analysis. But before I can do that, I also need to know how I can collect data. So just to start out on this page, the goal of data collection is to avoid bias. So I do not want preferred outcomes when I'm collecting information. I don't want to overrepresent one group or underrepresent a group. I want it to be as fair as possible. And one way I can be as fair as possible, at least in theory, in practice this is a really, really challenging thing to do, is I can do something called a census. And in a census, my sample is actually my entire population. They try to do something like this called the US Census, and that's got a lot of challenges to it because it's not practical to sample the entire US at any given time. Even just thinking about the fact that people are continuously being born and dying, and we're not going to be able to get a perfect head count. People might not have a static home address where they're able to get this information. They might not feel comfortable responding to the census. There could be a non-response bias to something about that. If I just wanted to know about my jelly beans that I have in my house here and I only had 7 jelly beans, then that's a really easy situation where I can just count and know everything. But usually censuses are messy, hard to do, and really time consuming. So the backup is a random sample. And you can think of this as being like names or numbers from a hat as an example. And random in general, this is a no bias way to collect data. So I put a whole bunch of numbers, like a lottery, where I have a big wheel spinning and I'm just pulling things out, like bingo night. That's an example of something that's random. If I asked you to pick your favorite number, not random. There might be certain numbers that come up more often than others. So for example, you might really like 17. And if I say pick a number from 1 to 20 and you're like 17 every single time, that's not random. In general, for random, you should not be able to predict what happens next. Convenience, this is exactly what it sounds like. You collect data in the most convenient way possible. So collecting data in the easiest way you can. So you go into a store and you ask the first 30 people you see, hey, what do you think about this store? That's a convenient sampling. You're collecting it all at once as fast as possible. That feels like it's related to group, and these next two ones are really, really group heavy, and I'm going to draw some pictures of them because the definitions are going to sound similar. For a cluster sample, I've got a whole bunch of groups here, and I'm going to sample all individuals in some of the groups. So maybe these are classrooms, and I want to know what PCC students think about parking, and I randomly sample some classes. Maybe I have some evening classes, maybe I have a daytime class, and I'm trying to figure out what's going on. I'm getting this in large clumps at a time, so that helps me get a lot of data. So cluster, I sample all individuals in some groups. Now the downside with cluster, I get a lot of information in a short amount of time, but I could be missing out on some really important opinions in these other groups here. So for example, maybe these are the daytime Monday students. And if I ask them what they think about parking and they can never find it, they might feel really differently than the Saturday afternoon students who can just park wherever the heck they feel like it. So if I sort of want to force that diversity, if I have a whole bunch of different groups, and I sample some individuals from each of those groups or each of those stratas, this is what it means to be stratified, forced diversity. This is sample some individuals in all of the groups. So cluster and stratified are kind of opposites of each other. Sample all from some, that's cluster. Sample some from all, that's stratified. Systematic, this is if I sampled every nth individual. So if I had a survey for every 10th person in the store, that would be an example of something that's systematic. And as a final type of survey technique, multi-stage, if I take any of the things above and I have it like systematic followed by stratified, or clustered followed by systematic, or systematic followed by a different type of systematic, if I have multiple steps to collecting my data, then I have a multi-stage way of looking at things. So surveys, we usually think of this as being like asking someone a question. I'm just thinking of it as a sample technique in general. If you are watching people without interacting with them, it's called an observational study. If you are controlling the variables to try to see what happens, so if you have inputs are explanatory variables, and you're trying to see what happens in response, that's an experiment. So for example, if I watch ducks at a lake, that's an observational study. If I go to the lake and I give them two different types of food to see if they like one more than another, that's an experiment. So observations, this is really hands-off. Experiment, this is remarkably hands-on. Let's look at a bunch of different techniques below and see if I can identify the data collection model being used. Randomly selects 3 classrooms and samples everyone in it. So I have a bunch of classrooms, and I'm sampling all individuals from some of the groups. This is cluster. Every 10th person on campus, how many credits they're taking. This is sort of a process or something that a machine could do. It's really system-based. It's systematic. I record the amount of time it takes for a goldfish in the fountain near building 2 to eat their meal every day. I'm just watching them. I'm not interacting with the fish. This would be an observational study. I want to know how many credits people are taking, and I ask some daytime and some nighttime students. So I have 2 groups, and to make sure I accurately represent these groups, I'm going to sample some people from each of those groups. Some from all, this is an example of a stratified sample. There's a lot of vocab. In fact, this entire first lesson is almost nothing but vocabulary. And I know that it takes a while to get used to this, which is why I'm giving you some early exposure here. I would continue to encourage you to practice this in the same way that you would a foreign language. Do 10 or 15 minutes a day just using some of this vocab until you get comfortable with it. Let's look at one example from start to finish using all of this information. And I've got two examples here. I'm going to leave the top one for you to try on your own. I'm going to do this bottom one. Cinetopia claims that 40% of customers use a Groupon to pay. Jesse sampled every 5th customer in that day and finds that 10 out of 20 of them used a Groupon to pay. Label each value using proper notation. So I have the claim that 40%, this is a claim for all individuals. If it's for a population, I'm going to be using a parameter for that. A parameter for a percent, it is claimed that 40% use a Groupon. In contrast, for a sample, so this would be a statistic of 20 individuals, 10 used a Groupon. My sample success rate, my p-hat, was 10 out of 20. That's my success rate. Written as a decimal, that's 50%. This is higher than what it looks like for that population claim. So I might think that there's a difference between these things, or I might think it's higher. So let's figure out how we want to phrase that question. Jesse wants to test the claim that 40% of customers use a Groupon to pay. State the null and alternative hypothesis. She thinks the actual value might be different. So she's not sure if it's more or less. She just thinks it might be different than 40%. So let's phrase this as a null and alternative. Null hypothesis is always some sort of a parameter equaling a number, in this case 40%. Alternative, it's the same symbol and the same number. I just have to change this inequality. And I will either have less if I think it's less than 40%, more if I think it's more than 40%, or does not equals if I think it's different. So I've now established what fair and not fair looks like. Let's look at the next piece of data that we're analyzing. How did Jesse collect this information? Well, she asked every 5th person. And if I'm looking at every 5th, that feels like something a machine could do that's systematic. If they've used a Groupon, determine what type of data this is. So they either used a Groupon or they did not use a Groupon. This is a yes or no question. This is word-based data. Word-based data is categorical, or the other word for that was it's equality, qualitative. So this is what I mean by just kind of bringing all of those pieces together to just figure out what the situation is going to look like before I start collecting data. We're going to look at more examples throughout the term where we actually find where some of these averages and standard deviations and graphs would come from to do the next steps. But now at least we have some of the vocab to get us going in the right direction. And I look forward to doing more of these with you throughout the term.